All right, we're looking at ridge regression, which is a way of reducing the model complexity to avoid overfitting when we perform a regression model. We're almost finishing it up, and I want to give the geometric interpretation of what it is that regularized regression or ridge regression is actually doing. So this is going to help us understand the differences between ridge regression and the next method of regularized regression, which is called lasso regression. So let's take a look at the geometry of regularized regression. So if you remember, the model theta r we're calling it, is the theta that minimizes this thing, which is the sum squared error, plus the penalty term, which is lambda times the sum of each of the square of each of the individual theta components. Okay, and this is the SSE here. And so what lambda is really doing here, it's a constant, it's deciding how much to trade off between fitting the data, right, that's the sum squared error, and having a low complexity model that is the sum of the square of the components. So it's a trade-off. Do we want to fit the data tightly, or do we want to have a low complexity model? Lambda is really what's controlling that that trade-off. So there's a second equivalent way of representing this problem. It's called the dual, and it goes like this. We could alternatively say that we're going to minimize just the sum squared error, okay, which is this guy. I need the transpose on the outside there. We're going to minimize the sum squared error, okay, subject to, or I'll just put ST, and we're not going to let the sum of the square of the components to get too large. So we're going to say that this model complexity has to be less than or equal to some parameter, and we're going to call that parameter t. So here we have a parameter in this formulation, right? And here we had a parameter in this formulation, and lambda is kind of playing the role of t and vice versa. So this is really what we're trying to do. We're trying to minimize the sum squared error, but we're not going to let our model become too complex. Okay, so this is just an alternative formulation, and t has to be greater than or equal to 0, just like lambda had to be greater than or equal to 0. So now let's just quickly decide on or examine the extreme values of t. If t were 0, then that means we're constraining the components of theta to be exactly 0. So this is the lowest complexity model. So t equals 0 is the low complexity, or the lowest, actually. Okay, and if t goes to infinity, then that's like saying there's no constraint on theta. So this is the highest complexity model, and that would be then, if there's no constraint on theta, then that's just minimize the sum squared error. So then we're back to the least squares solution. So remember over here, when lambda was equal to 0, that means there's no penalty, and then we have the sum squared error, or the least squares solution. That's the highest complexity. Okay, and when lambda is equal to infinity, that means a huge penalty on theta, and so that makes theta equal to 0, and that's the lowest complexity. And then we looked at that in the last video, okay? So now I'm going to give you a two-dimensional interpretation of the ridge based on this formulation here. So why 2 dimensions? Because I can draw 2 dimensions. So let's say that we have, so we're going to call this thing, inside the curly brackets, we're going to call that j theta, and we know that that's the sum squared error. So you give me a theta, and I'll tell you how good it fits. meaning the sum squared error. And if we FOIL that out, we get this, which we've done many times, particularly in linear regression. So we've got this here, right? If we FOIL this out, and this we can combine. We said that we've got the transpose of a scalar, which is itself basically. So we can just choose one of those forms and just add it to itself and get -2. And then we bring in our theta, our predictions. So this would be y transpose y -2 times x theta transpose, right? Because our predictions are x times theta, and so this would be x times theta transpose x times theta. And then if we FOIL that out, or if we bring the transposes in, etc., we have y transpose y -2 theta transpose x transpose y plus theta transpose x times theta. Okay, so this is what we've got. This is still just the sum squared error. Okay, now for two dimensions, so I can plot this. So I'm just going to write 2 dimensions. I've got y transpose y -2 times, and then theta would be theta 1, theta 2, right? 2 dimensions. And theta is normally a column vector, so when I take its transpose, I've got that. Then this is x transpose y, and then we've got theta 1, theta 2, and this is x transpose x, and then times theta 1, theta 2. So that's showing explicitly the 2 dimensions there. And then I'm going to call x transpose x. That would be a 2 by 2 matrix. X is n by p, or n by 2, so this is a 2 by 2 matrix. So we're going to call that Q11, Q12, Q21, Q22. Okay, and then what we've got, and I can write this out, kind of, it takes a little bit of space, but if I carry through the multiplication, I've got Q11 times theta 1 plus Q21 times theta 2. That's the first element, comma, gotta watch my thetas and my Q's, Q12 theta 1 plus Q22 theta, that should be Q, darn it, Q22 theta 2. Okay, so that's what I get when I do, that's this guy here. That's theta 1, theta 2 times x transpose x. So I'm kind of rearranging terms as I go. So this is a 1 by 2 times a 2 by 2, which would give me a 1 by 2. So there's the 1 by 2. So I still have theta 1, theta 2, right? And then I have this term. This is -2 times theta 1, theta 2 times x transpose y. And then I've got this constant term plus y transpose y. Okay, so I'm running out of room. I'm going to delete a few things here. Okay. All right, so I've got this. Now, let's call x transpose y to be, I'm going to call that psi 1, psi 2. Okay, just, it's constant, right? Because x is n by 2, so this is a 2 by n when you take its transpose, times an n by 1, that gives me a 2 by 1. So you give me the data, x and y, I can calculate that. Those are going to be 2 constants, and I'm going to call those constants, for lack of a better for lack of better, symbol psi1, psi2. Okay, so now if I plug that in down here, I've got j theta equals, if I carry out the multiplication, q11 q11 theta 1 squared plus q21 theta 1 theta 2 plus q12 theta 1 theta 2 plus q22 theta 2 squared. Then I've got minus, I'll draw that right here, minus 2 theta 1 psi 1 minus 2 theta 2 psi 2 plus, and then we've got y transpose y still. Okay, y transpose y. And y transpose y is just a constant, right? So now, why did we do this? Why did we carry out the multiplication? Because what we can do, right, we see theta, we've got theta 1 squared here, we've got theta 2 squared here. And then we've got the cross terms, theta 1, theta 2, theta 1, theta 2. We've got the linear terms, theta 1, theta 2, and then we've got the constant. So what we can do is complete the square. And so you can go back to your analytic geometry. But basically, you can write this in the following form. Theta 1 minus c1, where c1's a constant, squared, over a squared, where a is another constant, plus theta 2 minus c2 squared over b squared, where b is another constant, plus another constant c times theta 1 theta 2. Okay, you can complete the square and you can write it like that. Okay, and what is that the equation of? Do you know? So if I plot that, here's theta 2, here's theta 1. This is the equation of an ellipse. So this was all to say that the sum squared error, right here, the thing in brackets, is a family of ellipses. So you tell me what J is, and then I will draw the ellipse. And so one ellipse might look like this. So we might have something like this. Okay? So this corresponds to a certain value of J. We're going to call that value of J, J1. Okay, so if you give me a certain value of J, I've got this ellipse. And so what that represents is that everywhere on this ellipse, okay, if I walk around the ellipse, so I'm changing the combination of theta 1 and theta 2, but each combination of theta 1, theta 2 gives me the same sum squared error. That is, every combination of theta 1, theta 2 fits the data just as well as any other combination, as long as I stay on this ellipse. Okay, this is like going around a mountain where you change your latitude and your longitude, but the height of the mountain does not change. Okay, but certainly you can give me another J, right? Give me another J value, and that's going to be a different ellipse. So we'll call this J2. Okay, so if you give me a different value of J, maybe shown here is that J2 is greater than J1. All right, so now, again, any value of theta 1 and theta 2, any pair of theta 1, theta 2 on this ellipse gives me the same fit, the same sum squared error. Okay? But that sum squared error on J2 ellipse is larger than the sum squared error of J1. So that means, in terms of fitting, J1 is doing a better job. Anything on this ellipse is doing a better job. And we can draw really any sort of ellipse here. This is J0. But I can't draw an infinite number of ellipses, so I just show a few of them. All right, and so you can think of this as a mountain, but really it's kind of a valley, because we're minimizing the sum squared error. So right there in the valley, right there at the minimum, this is the ordinary least squares solution. Okay, that's the combination of thetas that minimizes the sum squared error right there. That's as small of a j as we can get. Okay, so that's the part in the curly brackets in the ridge regression formulation. Now, this thing, okay, so we just showed that this was a family of ellipses. Now this thing, the constraint, right? We've got now in 2 dimensions, I equals 1 to 2, theta I squared has to be less than some value of t. Okay, so if I expand this sum, this is theta 1 squared plus theta 2 squared is less than or equal to t. Okay, so now let's write this as the square root of t squared. If I choose a t, right, then this is the equation of a circle centered at 0 with radius square root of t. And actually it's a disk because it's less than or equals. So let me draw that disk. Okay, that's not a very good disk. Okay, neither is that. But you get the idea. Okay, and so when we choose a t, what we're doing is we're saying, okay, my model complexity, that is the magnitude of theta 1 and theta 2. Remember, we're trying to shrink theta 1 and theta 2. So when we choose a t, a parameter in the ridge regression, we're not allowing theta 1 and theta 2 to escape this disk. Okay, so this is like trying to find the bottom of the mountain, you know, the valley, but you're not allowed further from home so many kilometers or something. Okay, so where's the minimum? Where is the minimum then? How far down the mountain can you go? And the minimum is right here. It lies tangent. It lies on the border of the constraint, and it lies tangent to the ellipses. So this is the minimum right there. This is the ridge regression solution. So see, when you constrain theta, you are not allowing yourself to get all the way to the minimum, which is the ordinary least squares. And why are you not letting yourself get to the minimum? That's because that ordinary least squares has a model complexity that's large, right? We go further from home. That's a larger distance. And remember, the magnitude of theta was related to model complexity. Okay, so we're constraining the model complexity and we're trying to find the minimum of these ellipses underneath that constraint, and it's right here. And so that is the solution. That is the solution to the ridge regression, and that's the geometric interpretation. So that's it for ridge regression, and the next thing we're going to look at is still regularized regression, but it's called the lasso regression, and it's a little bit different. It has its own sort of geometry, and so we're going to use geometry in order to compare the two regularized regressions. So let's take a look at that in the next video.